Hello, everybody, and welcome to Black Hat. I appreciate everybody showing up for this talk. Today, we're going over HostSplit, which is exploitable anti-patterns in Unicode normalization. So I appreciate you guys joining us, and I want to go ahead and introduce Jonathan Birch. Hi, Jonathan. Can you give him a round of applause? Thank you.
Okay, so I'm Jonathan Birch with Microsoft Office Security, and this is HostSplit, exploitable anti-patterns in Unicode normalization. What I'm talking about today is essentially a new category of vulnerability. This is an attack pattern that I found to work against a broad range of software, and although this is a Unicode vulnerability, this is not a homograph attack. This is not about fooling human eyeballs. This is about fooling software bypassing security checks. Also, I want to emphasize that though I work for Microsoft and I'll be discussing Microsoft vulnerabilities in this talk, I've also found vulnerabilities of this type in a number of other products that are not Microsoft, and I'll be discussing those as well. I'm giving this talk because this is a vulnerability that works too well. This is something I'm hoping people in this room will go and fix. You probably have software that is vulnerable to this, or maybe you'll go hack someone else's software that's vulnerable to this. That'll make it better too. So here's an agenda for my talk. I'm going to give some background on how Unicode host names work, that's internationalized domain names, IDNs. I'll describe what I call the HostSplit attack, which allows an attacker to create a URL which is parsed as belonging to one host name, but resolved as belonging to a different host name. I'll then give you a rundown of an example exploit where I show how you could have used HostSplit to steal OAuth tokens from Office 365. I'll talk about other software I found that's vulnerable. I'll tell you what was vulnerable and what's still vulnerable. I'll explain host bond, which is a variant attack. It works against somewhat different software. I'll explain how you can test for these issues, either in your own software or something you're trying to attack. And I'll give you some best practices for preventing this issue or for fixing it. So I'm a penetration tester at Microsoft. I hack Office, Word, Excel, the services that go with those. So why am I looking at Unicode URLs? Well, a couple of years ago, I was at lunch with some other penetration testers at Microsoft, and someone mentioned, oh, you can now get host names in the .NET TLD that have have hieroglyphic characters. So you could get single character host names. And this was kind of cool. We all just went and got one over lunch, and I got this one. And yeah, that's a man riding two giraffes simultaneously. Maybe it's a metaphor for something. But this got me to thinking, how does this work? How do Unicode host names in URLs work? And well, in my position, I get to do some open-ended security research, so I spent some time looking at that. I looked to see if there were vulnerabilities in how Unicode host names are processed, and yes, there are. But in order to explain them, I'll have to give you the same background I learned. I'll have to explain to you a bit about how internationalized domain names, that's IDNs, work. So the first thing that's important to understand is that really the internet just runs on ASCII. So if you're doing a DNS lookup, if you're doing a same origin check, that's all done with ASCII. So IDNs, these internationalized domain names, the way they work is that every host name actually has two forms. There's a U label, which contains Unicode characters. It's nice for maybe showing a URL to someone in their native language. But there's a corresponding A label that's an ASCII string. And these have a direct one-to-one relationship with each other, and there are RFC-defined algorithms for converting between them. So there's to ASCII to go from the Unicode to the ASCII, and there's to Unicode to go from the ASCII to the Unicode. How those algorithms work is the crux of the vulnerabilities I'll be talking about today, so I'm going to give some details on those. So going from Unicode to ASCII, that to ASCII algorithm has two steps. There's a normalization step where you convert all of the Unicode characters to a standardized form. It's called a KC normalized form. And this is sort of like making a string lowercase before indexing it. It's to make it sort of standardized and comparable. And then there's a second step to convert the host names to ASCII. This is called punicoding, and you're going to take Unicode characters and convert them into an ASCII encoding. I'll detail those a little bit. So if you look at the characters on the left side of this slide, there's this A with combining ring above character, there's the angstrom symbol, and then there's an ASCII A with a combining ring above character after it. These all look the same, but someone trying to type this character might have typed any one of these. You really want software to treat them as the same thing, though. That's why the normalization step is there. So when you're converting any of these, to an ASCII hostname. You normalize them first, and these all normalize to this lowercase a with combining ring above character. Now there's a couple of important things to notice about this. First, in one of these cases, we've got two characters that become one character. Also, we've got an ASCII character with a Unicode character that just becomes one Unicode character. Both of those can happen the other way around also. You sometimes have Unicode characters that normalize to ASCII, and one character that normalizes to multiple characters. And I will get back to this step because it's kind of critical. After normalization, there's what's called punicoding. This is where you convert Unicode characters to ASCII. So if you look at this string, this is fiskmas, which is, I guess, the Norwegian word for seagull. This has a single Unicode character in it, which is that A with a combining ring above it. When this gets punicoded, you get the string at the bottom of the slide. This starts with an xn-dash, which is called an ace. That just means this part of the hostname is punicode. This is followed by the ASCII characters from the original hostname in the same order, so everything but that A with a ring above it. And then after that, you have a hyphen with this MUA. This MUA is actually a set of instructions for an RFC-defined state machine, which can be executed to put the A with a ring above it back in there. So those are just instructions that say, put an A with a ring above it between the next to last and last characters of the ASCII. Now, going the other way, going from the ASCII to Unicode is simple. You just run that RFC-defined state machine. So you just take that MUA and you run it and you get an A with a combining ring above it back in your string. Then you throw away the ace, and then you've got your hostname. You don't try to reverse the normalization because there's no way to do that. So you end up getting the normalized form out of this. Now, the RFC that defines how this works, the IDNA RFC says that when you take an ASCII hostname and convert it to a Unicode hostname, you have to then take the Unicode hostname you get, convert it back to ASCII again, and make sure it's the same thing you started with. Otherwise, you're supposed to go into some sort of an error flow, throw an exception, that kind of thing. But if you think about it, the average user scenario is never going to hit this. So you can imagine that some people implementing this might not have actually added that check. Well, there's one other thing to understand here, which is that there's 3 different standards for how all of this works. There's IDNA 2003, which was from 2003 and was the first way that IDNA worked. There's IDNA 2008, which tried to fix IDNA 2003 by not allowing as many characters and also changing the way certain characters normalized. But that caused a lot of problems for certain languages. This meant that in some cases you might have a hostname that under IDNA 2003 had one ASCII version, but under IDNA 2008 had a different ASCII version, and different people might own those. So then there was IDNA 2008 plus UTS 46, which tried to patch this by essentially adding a conversion layer before IDNA 2008. This said, well, we're going to take all the characters that IDNA 2008 treats differently, and we're going to try to convert them into what IDNA 2003 would have done, and then hand the whole thing off to IDNA 2008. The result is that none of these are really the same as each other. They're all a little bit different, and different vulnerabilities work on each one. So I've now given you some background on how IDNAs work, or how IDNs work rather, and now I'll describe what I call the HostSplit vulnerability. So if you remember that normalization step I mentioned, where all of those A's with rings above them became that lowercase a with a ring above it. Well, what if there were Unicode characters that when you normalize them, they became ASCII characters, but specifically ASCII characters that had syntax significance wherever you were going to use them, like say this. So here you have U plus 2100. This is the account of character. It's supposed to be used for addressing envelopes. But it turns out that when you normalize this Unicode character, it becomes ASCII A/C. So if you think about this, this is kind of a funny thing. That / is an important character in URLs. That's the path separator. So what happens if you use one of these characters in a host name, like this? So here we have evil.c account of.example.com. Well, if we run the to ASCII algorithm against this, if we do the conversion to make this an ASCII hostname, so we could do, say, a DNS lookup, you get this. You get evil.ca/c.example.com. And now, the punicoding doesn't happen because you only punicode when you've still got Unicode characters after normalization. So we just have this new ASCII hostname instead. And if you look at this, it started off as a subdomain of example.com, but now it's not. Now it's just evil.ca with a path. And presumably this is like some place where evil Canadian people hang out or something. But the hostname here has changed because of this normalization step. So that seems problematic, but Does that work? And yes, that works really, really well, unfortunately. It doesn't work as well as it did when I started doing my research, but I found this vulnerability in a lot of places. I first found this in Edge and IE, but I found issues also in .NET, Python, Java, and also a lot of other places I'm going to talk about today. I'll start with that Edge and IE vulnerability though. So it turns out that some websites will return HTTP response headers using UTF-8. And if Edge encountered an HTTP redirect response, say a 302, where the location header in the response contained Unicode characters, it would normalize those Unicode characters in the response header. So if you had this URL, this evil.c account of .example.com as a location header for a redirect, Edge and IE would actually just go to evil.ca instead. So that's clearly a bug. That's clearly not what you want the browser to do, but why does it matter? How do you exploit that? Well, I'll tell you how you could have stolen OAuth tokens from Office 365 using that vulnerability. So, a little background on OAuth, sort of a refresher. If you look at the OAuth authorization code flow, this is what you're going to use if you've got some website where you want users to authenticate to it, but you don't want to deal with usernames and passwords yourself. You're going to let some other service do that. So you redirect to that other service. You say, here's my application ID, and here's the redirect URI I want you to send an authentication token to. That other service is going to authenticate the user. Maybe they enter a username and password. Maybe they've just got a cookie. And then it redirects to that redirect URI with a token, probably in a query string, something like that. So this would be problematic if any website could start this flow and have the redirect URI go to itself. So if I could make my evil.com and say, oh, I'm going to redirect to, say, the Office Authenticator, and my redirect URI is evil.com, and my application ID is Office, it would be bad if the Office Authenticator just authenticated the user and sent the token to myevil.com, because then I'd have some user's token. This is prevented in OAuth by essentially having a allow list for where this redirect can go. For any given application ID, there is some pattern that says, well, these are the okay redirect URIs for this application. But how does that work? Well, in OAuth 1.0, it was really common to see redirect URI allow lists that were just star.something.com, like star.office.com. So if you had this URI with the evil.c account of .office.com, that ends with .office.com, so it's okay. It's important to remember that when software is dealing with URLs, mostly it doesn't think about, is this a Unicode URL or is this an ASCII URL? It just says, oh, I've got a string, it's a host name. Well, I'll do a regular expression against it. So normally, no one normalizes their URLs before doing these sort of security checks. So that comparison works, and you get a flow like this. You have some attacker website. It says to the Office Authenticator, well, okay, I'm office.com. I want to use the Office application ID. And my redirect URI is this evil.c account of .office.com. The service says, well, that ends with office.com or .office.com, so that's okay. I'll get a token, I'll redirect to it, and then it goes to Edge if you're browsing in Edge, and Edge actually goes to evil.ca, so it's not actually a subdomain of office.com, and evil.ca gets your token instead. But this is OAuth 1.0, and no one uses OAuth 1.0 anymore, at least not a lot of software does. Modern OAuth doesn't work this way. Modern OAuth generally has an allow list pattern that says it has to be this exact hostname, and often you'll see this exact path for a given application. So the attack I've been describing won't work for that. The attack I've been describing only works for essentially a subdomain check, something with a wildcard, and that's not what we've got anymore. But there is a tool we can use to get around this, and that's redirects. So in 2014, a researcher named Wang Jing publicized a vulnerability he called covert redirect, which said essentially, well, if you've got an OAuth authenticator that will send the token to some endpoint which also has an open redirect vulnerability, then maybe you can steal that token by essentially redirecting the token to your site. Maybe you can pull it out of the refer, or maybe you actually have redirect behavior that forwards the token. This didn't receive a really good, reception from the security community. No one seemed very impressed by this. But it turns out the HostSplit attack makes this much easier to do. It makes it much easier to find open redirects. And that is how you could have attacked Office 365. So office.live.com was a valid redirect endpoint for Office OAuth tokens. It also had redirect functionality that would try to redirect to any subdomain of dropbox.com. In combination, you could have used this URL as your OAuth redirect target to actually steal tokens. So if you look at this URL, the target here for the redirect once you get to office.live.com is evil.c account.of.dropbox.com. And that ends with .dropbox.com, so office.live.com said, well, that's okay, but it sent that as a redirect to Edge, and Edge said, oh, I'll go to evil.ca. And that's where the token got forwarded to. Except this didn't quite work because we were lucky. It turned out that some of our middleware had a UTF-8 double encoding bug, so that any UTF-8 response header actually got UTF-8 double encoded. And so that redirect actually went to evil.c and a bunch of garbage.dropbox.com. And it turns out that browsers wouldn't even do that. But this put us in kind of an awkward position. This meant we had a bug in our middleware that we couldn't allow to be patched on our middleware until we fixed Edge and IE. So we actually had to monitor the patches for our middleware to make sure that this didn't get fixed or that we didn't accept a patch where it got fixed until we fixed our stuff. Okay, so that's how the vulnerability works. What's vulnerable to this? Well, first, it's not just the example I gave. It's not just OAuth. Host names are security identifiers. There's a whole RFC about if you misinterpret security identifiers, bad stuff. This can do lots of different things because a lot of places host names are used to essentially decide whether something is an okay place to do something. It's also not just Edge. I found this vulnerability all over the place. I'll be going through a lot of different places later in this talk. And it's also not just this account of character. There's a really long list of Unicode characters you can do this trick with. I've got them at the end of this slide deck. It's also in my white paper. Here's a few examples though. So like an interrobang character normalizes to question mark exclamation point. So it pushes everything after it just into the query string. A full width solidus character turns into just a /, full width number sign becomes number sign. Full width @ becomes commercial @, which is nice for attacking email. So there's a lot of possibilities here. It's also important to understand that the specific IDNA version that's being implemented in software matters. Pure IDNA 2008 is not vulnerable to HostSplit. Pure IDNA 2008 does not allow any of the characters that let you do these shenanigans. IDNA 2003 or IDNA 2008 plus UTS-46 are vulnerable though. However, in both of those cases, there's a flag you could have used, which was use std3 ASCII rules, which says essentially when you normalize a host name, make sure afterwards the host name only contains characters that are supposed to be there in host names. But nobody uses that flag. And nobody uses pure IDNA 2008. And why do they not do that? Well, it's because of underscores. So the std3 rules for URLs from way back, old RFCs, say that a host name can only have alphanumeric characters, dashes, and periods. But it turns out that lots of old URIs, especially intranet host names, have underscores in them. And if you use the std3 ASCII rules, you just can't talk to host names that contain underscores anymore. And that wasn't really acceptable to anyone. So no one uses this flag, and everyone's vulnerable because they want to talk to host names that have underscores in them. That said, browsers at least are safe now. I reported the Edge and IE vulnerability to MSRC. This was patched in February. Now it's the case that Edge and IE, when they encounter an HTTP redirect like this, they just won't redirect. If the location header has one of these characters in it that would suddenly change to something with syntax significance so the host name changes, the redirect isn't followed. Firefox and Chrome never had this bug, so they've always been safe from it. Safari does something very strange where if it gets a UTF-8 location header for a redirect, it percent encodes it and then does a DNS lookup on the percent encoded version, which doesn't work. So I don't know what that's about. It's probably not exploitable, but maybe someone can figure out something they can do with that. But other Microsoft stuff was vulnerable as well. .NET was vulnerable. So the .NET framework has classes for dealing with URIs. It has the URI builder, which can be used to pull the hostname out of a URL. And it has the IDN mapping class, which can be used to convert a hostname between Unicode and ASCII. And it turns out that if you used URI builder on one of these hostnames, so this canada.c account.of.products.office.com, it would say, well, the hostname is that whole thing. But then if you used IDN mapping to convert the hostname from Unicode to ASCII, so you could say do a DNS lookup, make a request to this URL, well, suddenly the hostname is actually now canada.ca because it would do that normalization for you and there was nothing that said this wasn't okay. This meant that if you're writing software that's dealing with URLs, and you're probably just dealing with the URL as a string and probably doing comparisons on it without trying to convert it to ASCII, you would do the wrong thing. You would see a URL as being a subdomain of some hostname, but it wasn't. And then when you tried to make a request to it, you would make a request to something else. This is also fixed now. I reported this to MSRC as well, and this was also patched in February, and it was backported, so even .NET 2.0 is good now. The way it works now is when you've got a hostname and it's going to be converted to ASCII, then they pull out just the hostname, they convert it to ASCII, they say, well, does the hostname we ended up with have characters in it that shouldn't be in a hostname? If it does, throw an exception. So the code on that previous slide now shows a system.uri format exception. Fixing frameworks is a big deal because a lot of stuff was vulnerable because .NET was vulnerable. An example of this is Fiddler. Fiddler was a product made by Telerik. It's an HTTP traffic monitoring tool. A lot of people use it to do penetration testing, but also just testing software that talks to networks. And it turned out that if you were running Fiddler, every browser was vulnerable to hostsplit redirects. Because Fiddler would do the thing where it would intercept that HTTP redirect response, it would take the location header, and it would normalize it for you, and then hand the normalized version off to the browser. And so Chrome and Firefox would also have the wrong redirects if you were running Fiddler. But they didn't have to fix anything. We fixed .NET, and because the framework is better now, because the classes they rely on are fixed, Fiddler no longer has a vulnerability either. But .NET was not the only vulnerable framework. Python was also vulnerable. So in Python, there's a built-in library called urllib, which is used for parsing host names and things out of URLs. And Python also has encodings where you can map host names, say, from IDNA to UTF-8 and things like that. And this is essentially the same vulnerability that .NET had. If you tried to parse the host name out of a URL where you've got one of these host split characters, so here it's canada.c account of.microsoft.com, it would say the host name is that whole thing. It wouldn't break it where that host split character is. But if you took that same URL and then you said, well, I want to convert the host name to ASCII so you can do like an actual request to it, well, that A over C becomes A/C. And now when your request is made, it's going somewhere else, and the host name is something different. And I need to share the credit for this vulnerability with Pani. He was an intern at Microsoft. When I found this, he helped me work out the details in Python. We actually did this at a hackathon a while back. Now, this was one vulnerability in Python that was similar to .NET, but Python actually had a different vulnerability as well. So the issue I've been talking about here allows you to essentially make something that was a subdomain of some URL or some hostname and now isn't. But Python had a vulnerability that let you just swap the hostname in a URL. And it worked like this. So here we're using the sort of old school basic auth syntax. You've got username : password at some hostname, except the username here has a full width number sign in it. And the trick here is that before the normalization happens, that full width number sign is just part of the username. So the hostname is actually the thing after the at. And that's what Python will tell you it is. But once you normalize this, well, it turns out that the username would also get normalized. And that full width number sign becomes a pound sign now. And so everything after it is the fragment. And the hostname is just whatever was before it. So in this case, the hostname goes from being products.office.com to being bing.com. I reported both of these to Python, and they fixed both of these. They were different CVEs, but at this point, if you're using Python, you should be okay. Python was not the only third-party framework that was vulnerable either, though. Java also had this issue. And I'll give you a second to look at that while I take a drink. But this is essentially the same vulnerability that .NET and Python had, where here we're using the URL class in Java along with the IDN class. We're pulling the hostname out using the URL class. And before we convert the hostname to ASCII, the URL here is again going to have the hostname be the whole thing, the evil.c, and this is the account of character, .microsoft.com. But after we use the IDN.toASCII method to convert the hostname to ASCII, which you have to do in Java if you want to make a request, now the hostname is evil.ca. I reported this issue to Oracle, and this was fixed in July. I haven't had a chance to review the fix because this was pretty recent. But hopefully this is good now as well. Okay, so that was a bunch of frameworks, but what if you're writing native code? Well, if you're writing native code in Windows, your code probably is vulnerable. So if you're using IDNA to ASCII to convert a Unicode hostname to an ASCII hostname, that Windows API will actually also convert the accounted character to A/C, and all of the other characters that I mentioned that also let you do these tricks work as well. But this is necessary. IDNA to ASCII is an RFC-defined algorithm. There are things that it's used for that are not host names. If the behavior of this changed, a lot of other things would break. It does have a flag, which is the use std3 ASCII rules flag I mentioned before. If you use that, it is safe, but then it won't accept host names with underscores, so there's a trade-off there. You'll have the same issue if you're writing native code in Linux. So in Linux, there's the GNU libIDN and libIDN2 libraries, which are used to convert host names between Unicode and ASCII. And in both cases, they will also convert account of to A/C, and all of the other host split stuff works as well. For libIDN, you can fix it by using the use std3 ASCII rules flag. For libIDN2, you can use no tr46. Again, no underscores if you use those flags. I did contact the maintainers of libIDN about this in February. They said it was by design, and I agree. They're in exactly the same boat as Windows is with this. This is an RFC-defined algorithm. They can't change how it works either. Okay, so that was HostSplit. And that only worked against IDNA 2003 or IDNA 2008 plus UTS 46. But I've got a different attack that works against pure IDNA 2008. So IDNA 2008 doesn't allow any of the characters that enable HostSplit. It won't normalize them. But it does allow two characters that the other two specifications don't. And that's the zero with joiner and the zero with non-joiner characters. IDNA 2003 doesn't let you use these in host names because they're invisible. So you would have the problem where a user couldn't tell the difference between some host name and the same host name plus an invisible character somewhere in it. But it turns out that these characters are important for rendering certain languages. For languages that use Devanagari as their script, for instance, they change the way the ligatures work. So IDNA 2008 allows these characters in host names, but conditionally, only if the joiner character is between two characters that would render differently because it's there. So if you put one of these characters in a hostname, if you just make some hostname like micro and then a zero with joiner soft.com, and then try to use IDNA 2008 to convert it to ASCII, that won't get you anywhere. It'll just throw away the zero with joiner, so it's just Microsoft.com. But you remember what I said about the round trip check, that when you're going from ASCII to Unicode, you're supposed to go back from Unicode to ASCII and make sure you ended up with the same thing. Well, that isn't really implemented very often. So it turns out that in IDNA 2008 implementations is often the case that if you write your own software to do the punicoding and put a punicoded zero with joiner in there, they're okay with that. So you can make a hostname like this. This is xn-microsoft-469d.com, where that's got a punicoded zero with joiner between micro and soft. And most IDNA 2008 implementations were happy to accept that hostname. But that's problematic. So there's two issues here. First, you've got this ASCII hostname, but if you're going to show this to a user, you're going to convert it to Unicode again. And if you do that, well, then it just looks like Microsoft.com. There's a zero with joiner somewhere in it, sure, but it's an invisible character the user can't tell. And also, if you remember what I said about zero with joiners getting thrown away when you go from Unicode to ASCII, that's what happens here. So if you convert this hostname from ASCII to Unicode, then back to ASCII, it's just Microsoft.com. So you've got hostnames that essentially mutate. They go from not being something to actually being something. And that is exploitable. So the hostbond vulnerability, as an example, say you've got some email server out there that's at email.somecloudhost.net that you want to impersonate. So you go register your own domain and you stick a punicoded zero with joiner in it, but it's otherwise the same as theirs. So you make this xn-email-xt3b.somecloudhost.net, where that's got a punicoded zero with joiner between the E and the M. What happens if we send email from that server? Well, let's say we set the server up. We go use Let's Encrypt to get a certificate, because you can. They're okay with anything that's an ASCII hostname. And if you can set actual DNS records, you can set up DKIM, SPF, DMARC, make it all look legit. You send email from this to Gmail, and Gmail will decode the punicode, and it will show it as coming from the server you're trying to impersonate. So xn-email, etc. will just show up as email.somecloudhost.net in Gmail. They do the SPF and DKIM checks, but they do it on the ASCII before doing the decode, so it looks legitimate, but it's not. And then if you try to reply to that email, Gmail will throw away the zero with joiner again, and then it goes to the real thing you're trying to impersonate. So it lets you do kind of an interesting phishing attack. You can send email as anybody, but you can't receive the replies. I did report this to Google in February. They've acknowledged the issue. They've said that they're monitoring their services to make sure that no one is exploiting this attack against their users. It's still there, though. Also, besides Google, besides Gmail, libidn2 was also vulnerable to this hostbond issue. If you take that same hostname with the punicoded zero with joiner in it that I described, the one where it's micro zero with joiner soft.com, and you tell libidn2 to decode it, or if you did, then it would do that. And you would get Microsoft.com with a zero with joiner in the middle of it, which you can't see. If you're in Bash, you'd probably get a box and you'd notice, but if you're in a GUI, you probably wouldn't. I did report this to the maintainers of libidn, and this was fixed in libidn2 version 2.2.0. As far as I'm aware, the only distro that uses that right now is Debian Unstable, so you might want to talk to whoever maintains your distro to get them to pick this up as well. And I need to share credit for this vulnerability with Tim, Florian, and Nikos. They helped work out the fix for this. They helped work out additional test cases. They made sure fixing this didn't break anything else. So thanks to them. There are a lot of limitations on this hostbond vulnerability, though. First, like I said, it only works against pure IDNA 2008. IDNA 2003 does not allow zero with joiners and so on. It's also only ever going to be exploitable where you've got software that takes a URL that could be an ASCII URL that's punicoded, and it's going to decode it to Unicode. And usually that only happens if it's displaying it to a user. So this is usually only exploitable if there's a GUI somewhere involved. Most significantly, though, you can't get host names like this. If you go to a domain registrar, like say, I don't know, GoDaddy or something, and you try to get like that xn-microsoft, etc.com, they'll just say no. Some of them think they can get it, they'll take your money, and then later they say, oh, no, we couldn't get that. So you can't get host names like this from domain registrars, but providers of third-level domains generally do let you get these. There's lots of services out there that will let you buy a subdomain of their host name, and those services generally don't care about whether the punicode in your ASCII subdomain is actually not punicode you're supposed to be able to use. So that's how you attack this sort of thing. Okay, so I've described HostSplit and HostSpawn. How do you test for these issues? Well, testing for HostSplit is pretty easy if you can monitor network traffic. If you've got some application running on your machine, you can see what requests it's making. Then all you do is you give it a URL that has one of these magic HostSplit characters in it, and you see what kind of DNS lookup it tries to perform. If you use a URL like this canada.c accountof.bing.com, what you want to look for is a DNS lookup for canada.ca. That means it's actually decoding that character in the hostname into ASCII and then making a DNS lookup for the wrong thing. The ideal result for this sort of a test case is that it just doesn't make the request. But if it makes a request or a DNS lookup for some weird punicoded subdomain of bing.com, that's also okay. It's not ideal, but it's probably not exploitable. If you can't monitor network traffic, though, there's a somewhat more complicated test case that you can use. And that's this. What you can do is you can go and register a couple of domains, and here I'll call them a.com and b.com. And for b.com, you'll make a DNS wildcard record that says all subdomains of b.com go to the same server. And then for both a.com and b.com, you'll set up servers that will just record all the network traffic that goes to them. Then you'll give a URL like this to the thing you're trying to test. Say it's someone else's web service, where it's a.com and then a full width solidus and then like x.b.com. And what this is going to do is, if this is vulnerable to HostSplit, the software that you're looking at, it's going to decode that full width solidus into a /, and it will try to make a request to a.com. If it's not vulnerable, it either won't make a request or it'll make a request to b.com. And since you're recording network traffic on both servers, you know which one of those it did. This lets you test things that you can't directly monitor the traffic for. Hostbond is a little more complicated to test for. For Hostbond, you need to consider cases where there might be an untrusted URL that's provided to your software that's going to be converted to Unicode. This usually means that someone's providing you a URL that's going to show up inside of a GUI somewhere. And once you've identified the cases where that's going to happen, there's a lot of different test cases you need to try. So there's the zero width joiner I mentioned. So you can use a puny-coded zero width joiner, and there's an example here. And that should not be rendered as a zero width joiner. That should always either show up as puny-code, not be rendered, but it should never happen that it just turns into something that looks like it's not there. You can also, or you should also test what I'm calling the bubble numbers. These are Unicode characters that are essentially numerals with circles around them. They normalize to just ASCII numerals. So sometimes you'll see essentially a two-step normalization. And for those, what you want is essentially that it's either rejected or it shows up as puny-code. It shouldn't show up as the circled numeral, and it should not show up as just an ASCII numeral. Finally, there's the Greek question mark character, which is kind of a magical Unicode character that lots of software likes to turn into semicolons, even if it's not trying to do normalization for complicated reasons. So you can puny-code one of those, and if you stick that in a hostname, it should never look like a semicolon. Anything that looks like a semicolon from that puny-code is a vulnerability. And this is the sort of thing that you might use to attack lists of hostnames, or maybe email, where you have semicolons to separate different things. And you also need to remember that the host spawn vulnerability is not just a web vulnerability. So I explained earlier how this could be used against email, but host spawn can also be used as an attack against IM protocols like SIP, or other network protocols that use host names, either directly or in email addresses or something like that. One useful test case for host spawn, if you're using it with, or trying to test email, is to essentially send email to an email address you control, but add a second recipient, which has one of these bad puny-code host names in it. It probably won't receive email, but you can see what it looks like when you receive the email. And if that second recipient shows up with the bad puny-code decoded, that's also a vulnerability. Okay, so that's how you test for this. What are some best practices for preventing this vulnerability or fixing it in your software? Well, first, and this is something I really want to emphasize, software needs to make all of its decisions about host names using ASCII. Most software, if it's dealing with a host name, has something that's just a string, some type called string maybe. And it's not thinking about, well, is this an ASCII URL? Is this a Unicode URL? So if you're doing some sort of a comparison or a regular expression against a host name, before you do that, you must convert it to an ASCII host name. If this is something you can set as a security policy, it's a good rule. Only compare host names as ASCII. Lots of code does this wrong. Lots of platform code does this wrong. This is really pervasive as a vulnerability. Second, if you're doing conversions in your own software between Unicode and ASCII host names, you need to use the std3 ASCII rules flag. If you're using the std3 ASCII rules flag and you try to convert a Unicode hostname to an ASCII hostname and it's going to introduce some syntax character like a /, it'll just fail. This does mean that you can no longer talk to hostnames that contain underscores. You might want to set a policy that says we don't make hostnames with underscores anymore. It makes this issue easier to fix. Finally, you might have code that relies on platform code that's already vulnerable. There's lots of APIs out there that are vulnerable to HostSplit. What you can do is write a wrapper function that says, before I call this API, I'm going to make sure the URL I pass to it isn't going to cause a HostSplit vulnerability. So what you can do is essentially do an ASCII conversion yourself on just the hostname and see if the hostname you end up with contains syntax characters. Or you could just use the std3 ASCII rules flag when you do that before you pass it off to the platform code. For the other side of things, for host spawn vulnerabilities, you need to worry about cases where an ASCII URL is being passed to something, maybe just a URL, a string, that's going to display it or otherwise deal with it and might convert it to Unicode. A lot of times this is going to be controls of different sort that you might be using. If you're going to pass a hostname off to a control, what you want to do is essentially try converting it to Unicode if it's puny-code, and then convert it back to ASCII and make sure you end up with the same thing you started with. If the hostname you end up with at the end isn't what you started with, you want to just throw away the URL, not hand it off to the control, not hand it off to the API. So your wrapper function prevents the bad thing from happening. So I'm hoping that people in this audience, people who see this talk, go and make this better. Please test your software for Unicode normalization vulnerabilities. Please only compare host names as ASCII. Make a policy for that if it's something that you can do. And if you're someone who attacks things, if you're on the other side of things, please go get bounties with this. This vulnerability has worked in almost everything I've looked at. And so I'm expecting it still works in a lot of things. I haven't looked at all the software out there. I haven't even looked at most of the platforms people build web services on. So there's probably lots of places you can go and get fun CVEs, maybe some money out of this. And if you do that, people will pay attention, and this will also start to get better. And that's my goal for the day, and that's all I had to say. So are there any questions from that?